All right, everybody, this is week 6. We're back from midterms. Hopefully we're happy with our midterm grades. And we're starting with regressions. So this is our first lecture on regressions. This is similar to chi-squared because regressions allow us to not only see what's happening in the sample, but what's happening in the population. And so really we're just taking what we've already learned in the first half, and for the rest of the second half, we're looking at regressions. Okay, so we're gonna take baby steps, as hopefully we always do, and we're going to start with bivariate regressions. Bi means 2, 1, 2. And so after bivariate regressions, we're gonna look at multivariate regressions, more than 2, multiple. And so let's begin. All right. Okay. So, let me do this first. Shit, I should have done that first. Okay. So, with regressions, we're comparing relationships, right? So we've already, since lecture 3, we've been talking about relationships. We have graduated beyond ourselves to learn about relationships. And so we will continue in that vein. And just like we did with contingency tables, darn, it's not here, but we looked at contingency tables, which helped us look at categorical variables and their relationship, right? We also looked at correlations to understand interval variables and their relationship, right? And now we're going to do the same with regressions. But the thing about regressions is that it allows us to be a little bit more specific. It gives us a numerical description of how both of the variables vary together, and allows us to make predictions based on that numerical description. So as we looked at correlations, we were able to say that men, have higher salary than women, or whites have higher salary than blacks. All of this very sad, right? But it's the truth. And we'll work on that through policy, right? But anywho, we were able to say that the more education you have, the higher your income, these types of things. But with the regression, what it's going to allow us to do now is to say how much, by how much. So it's not just increasing, but by how much. It's not just higher, but by how much. So that's where we get into these predictions. And so let's begin. Let's continue. All right. So regression equation, nothing to be scared about, nothing to be alarmed about. Regression equation is what it is, and we're going to learn what every single bit of this equation means by the end of this lecture. So y hat equals b naught plus b1 times x. Y hat is the expected value of the dependent variable. Y hat is our dependent variable, and in mathematical terms, expected means hat. So y is our dependent variable, hat means expected in mathematical terms. So y hat is our expected value for our dependent variable. We know what equals means, so let's go to x. X means our independent variable. So y, dependent variable, x, independent variable. Notice it's not expected, so we don't see here x hat. Okay, so I should have closed my door. So x is the value you choose as your independent variable. So if you are choosing for age and you decide to choose 12, then in that equation, what would you type? 12, right? So b naught and b1 are constants that result from the regression analysis. So we're gonna, just like we've done with contingency tables, specifically with correlation matrix, it spits out some numbers to us, right? Our b naught and our b1 are those numbers in the regression that it's gonna spit out to us. And so we'll learn in the next couple of slides what those two mean. But for this slide, it's important to take away that y is dependent variable, x is independent variable. Boom, done. Okay. So now we look at our b naught. B naught, you see b0, we say b naught, and that is essentially our y-intercept. Our y-intercept is the expected value of y when x equals 0. So when we look at this equation, we should be able to see that with x equals 0, then x times b1 means that all of that whole thing is 0. So essentially, y hat is b, right? B naught, excuse me, b naught. So that's all it's saying, right? So if you take this x naught, excuse me, x, and you make that 0, then this whole b1 times x, that whole thing goes to 0. So b naught is y hat. Therefore, that second bullet is telling us that b naught is the expected value of y when x is 0. Just like that. Okay, so we use these notes. We're going to come back to it because while we're saying it, while I'm saying right now, and it makes sense, you're not going to necessarily, you might not remember it the first time. And trust me, I've been doing this since 2012. You won't remember it the first time, so don't forget your notes. Don't forget the slides that are here for your benefit, okay? Never a need to guess about any of this. You just come to the notes, remember it, and commit it to memory so that you don't ever have to come back to the notes, but you'll get it over time. So B naught, this is sort of math lingo again, but B naught, if you remember any algebra from back in your day, is the point where the regression line crosses the y-axis. So if y is 0, ooh, maybe I should draw it. Let me see if I could draw it. Oh, I don't know. So say we have our x and y, right? So this is y. I'm drawing. This is x. Okay, so of course this is 0, right, for x and y. I can't write 0, I don't think. That's going to be tough. Okay, there we go. So if x is 0, right, and y, then our b naught is whatever is left, right? If b naught is 3, then x is going to be, then y, so if x is 0, right, b naught is going to be, and b naught is 3, then our y hat is the point where the regression line crosses the y-intercept, right? So our b naught, if that said 3, then this is essentially what it would look like on a graph, right? If our b naught was 45, right, and we don't care what b1 is at the time because it's being multiplied by 0, so what's left is 45. So what do we know? We know that our b naught is our expected y because x is 0. So our b naught is, if it's way up here or something, 45, and so, you know, or maybe it's a much flatter line. But either way, it's gonna cross right there at the y-axis, at the y-axis. I don't know why I can't draw circles, but there we have it. Turn my phone on silent because I'm popular. Okay, so I'm not, but still. All right, let me clear this out. And then the last point to make is that this value, b naught, is only meaningful when x can have a realistic value of 0. So if x is what's your salary at 0 years old, well, you're likely not to be working at 0 years old. So that's not even a realistic number. So we will always have a B naught. We will always have a B naught. Let me draw a circle there. We will always have that, but it might not always mean something. And we'll see when it does mean something and why it would mean something in those instances. Okay, so moving on. So here's an output. Here's an output, a regression output. So we see here that our dependent variable, it tells it to us. Excel doesn't tell it to us, but it's okay because we run it, and so we know exactly what our dependent variable is that we ran, and so all we have to do, just so that we remember, is just type it under there, under the output, type dv equals whatever it is that was your dv. Okay, so constant, this is highlighted here because that is what this entire slide is about. This entire slide is about what is y-intercept. Y-intercept is b hat, b naught, and b naught is the value of x, the y-intercept is b naught, and b naught is the value of y when x is 0. Okay, and so we see here that our b naught, you'll see this is an SPSS output, but in Excel, it'll actually say intercept. So guess what? There's no guessing. So you'll know exactly what your intercept is because Excel will say intercept, where you see here it says constant, and it'll show you the number next to it. So whatever number is next to the word intercept or constant is your y-intercept, is your b naught, okay? That's one thing to note. Another thing to note, the reason why, say, other softwares might call it a constant is because there's no number being multiplied by it. We see B1 is not a constant because it's being multiplied by something else. A constant means it's, the number is the number, as is, nothing can change that number. Okay, so we call it a constant. You might see it as a constant. You might see it as a y-intercept. You might see it as b naught, but in all cases, nothing changes it, right? I mean, besides the actual data that generated the number. Okay, so we know what our DV is, dependent variable salary, and it's being measured in dollars. We know that our constant is negative. If it's salary, right, our constant is negative 5,000, $132.76, right? So that is what we can see based on this output, this regression output. It's telling us that our B naught is negative 5132.755. But what does that mean? Well, without even clicking on the next slide, we just look at the second bullet. The second bullet tells us what it means. It tells us that that number, negative 5132.755, is the expected value of y. And now we're not saying y because we actually know the name of this y. Y is called salary. If I know your name, I'll say your name, right? If I don't know your name, I say ma'am, I say sir, but I know your name, right? You're not student X. You are whoever you are. You have a name. So we're never, ever, 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 ever going to say X and Y whenever we're creating this equation, right? We're never going to do that. We're never, because we know the variables. We just know, we know the names. So here we go. Again, sorry. Where was I? Our B naught, our y-intercept is telling us that it that is the expected, and here we are, bullet 2, expected salary, value of y is salary, the expected salary when, what is our x? Our grade equals 0. And so before I even get there, I just realized that I didn't give the equation. Duh. So here's the equation. So the equation, expected salary, we can say salary because we know your name now. Your name is salary. Your name is no longer Y hat. Your name is no longer student X or student number 3. You have a name. So expected salary equals B naught plus B1 times grade. Why is it grade? Because grade is right next to that B1 we see, and our X's are listed here after the constant. All of our X's are listed under the constant, okay? So where are we? So here's our equation. So we can specify even more because we have this first part of the equation, but we can specify even more because we now have this output. So this output is telling us that the expected salary equals B naught, which is negative 5133, plus B1, which is 4779 times grade. This will be intuitive, right? Because we know that B0 And then the next thing is B1. So B0 we see as the constant. So wherever the constant is, that's our B0. Wherever it says intercept, that's our B0. So if we're counting correctly, the next number should be 1. So right under 0 is 1. So B1 is 4779. Okay? And we multiply B1 times the variable beside it. So what variable name is beside it? Well, I don't see the word X, the letter X. What I see is grade. So grade is the independent variable. Okay, so grade is the independent variable. So we have our equation. So here we go. The y-intercept, as I already said, tells us that the expected salary for employees at grade 0 is B naught, negative 5133, rounding up. Okay? So first, there is no grade 0, right? So if we look at that very last bullet, the value is, this y-intercept is only meaningful when x can be a realistic number of 0. Okay? So there is no grade 0 because we know that the federal grade scale, the general schedule, starts at 3. So 0 is not really a realistic grade. So it makes sense. That's why if you have a grade 0, you would be essentially paying the government back $5,133. So it's not tax season. So hopefully you are getting money back and not giving money away to the government. But that's what this third bullet tells us, that if there were a pay grade 0, the negative sign on the y-intercept is telling us that those employees would essentially be paying government in excess of $5,000. Therefore, in this case, in this particular case, the y-intercept means not a lot because it's not realistic. It's not a real number, so it's not relevant. Okay, moving on. Back to that same equation, y hat equals b naught plus b1 times x. So note that I say generic here because you know that once we do know the variable names, we're no longer going to talk in terms of student 1 and Professor X. We're going to say Dr. Uzuchukwu. We're not going to say yo, you, right? Or you, yeah, you as in Uzuchukwu. Okay, so anyways, so now we're looking at B1. This slide, last slide was about B naught, the y-intercept. This slide is about B1, also known as the regression coefficient. As you can imagine, it says regression coefficient. That's what this entire lecture is about. Therefore, that's what this particular B1 number means everything to a regression. And so it's important for us to understand how to interpret this regression coefficient. So here we go. B1 is the expected change or the expected difference in y. We know what y is, our dependent variable. So B1 is the expected change or difference in the dependent variable for every 1 unit increase in x in our independent variable. So if our independent variable goes from a pay grade of 9 to 10 or pay grade of 10 to 11, what's going to happen to our dependent variable? It's going to change by whatever that number is that B is. Whatever B is, that's what it's going to change by. So our B1 tells us direction, our B1 tells us strength. Guess what? We're already, so I'll say it tells us strength, but we'll look at lecture 8 and see really what it's telling us about strength. So, but we'll table that strength discussion for another time. But it does tell us some level of impact, right? Some level of association about X and Y. So in terms of direction, we know we look at the sign if it's, that's in front of the B. If it's a plus B1, positive relationship between X and Y, dependent and independent variable, right? If it's a negative, a minus sign, right? We know that would therefore be a negative relationship. As X is going up, as our independent variable is going up, what happens to Y? It starts decreasing, right? opposite directions. So strength, well, let's take a look. That's this point that we make in the second bullet. So the expected change of X when, the expected change of our Y, our dependent variable, whenever X increases by 1 unit. And this is not just happenstance, okay? When I say 1 unit, I need you to say 1 unit because we're not just saying arbitrarily any unit. It has to be 1. Go figure. A regression, regressions are only about 1. Only about 1. And you have to be very specific and say 1, because we can't just say as age increases, as education increases, as grade increases. No, as it increases by 1. Because now that we know that what X is increasing by, then we can be, what we say about Y, because we are being very specific about Y, it's going to increase by whatever B is. That's what we're saying in this bullet. So if we're going to be that specific about Y, we need to be very clear about what X is actually doing. What is X doing? It's increasing by 1 unit, whatever that unit is. If it's years, if it's grade, if it's height, whatever the 1 is, inches, whatever that unit is, that's what X is doing. Our independent variable is doing. And it can only do that. It cannot do 2. 1. Okay, so here we have, hopefully, our equation. You were able to figure it out without me putting it up here, but here it is anyway. And so now notice what's being highlighted. Not constant anymore, because in this slide we're talking about regression coefficient, our B1. Okay, so our B1 is telling us that our regression, our X, first off, our B1 has to do with our X, the only X that we see here. Notice it's only 2 variables, as I said at the very beginning of this lecture. The 2 variables, salary and grade. Salary, grade, that's it. It's only 2 variables we're dealing with. And so our Y, our dependent variable, is salary. Our X, our independent variable, is grade. And so now what is the regression coefficient for grade? Well, the regression coefficient for grade is 4997. Well, what does that mean? What does it mean? Well, we're going to give a couple of interpretations. They mean the exact same things, right? But you have to, as part of the learning process, I think it's important to share with you all the different ways you can say something. And these are only 2, so that you know that it's not just one way to carve a turkey. Right, so here we go. As the pay grade of a federal employee increases by, you guessed it, 1, say from 10 to 11, 11 to 12, 9 to 10, whatever. As it increases by 1, the pay grade, the person's salary increases by $4,779. Okay, notice that this 4779, just like the negative 5130.32, all of that has to do with dollars, with salary, because that's what this equation is all about, right? Even though grade is not about dollars, it's just about, are you paid grade 11 or 12 or 3 or 5, right? But everything when we're interpreting has to do with dollars. So as one's pay grade goes from here to here, goes up 1 unit, right? Federal employees earn $4,779 more. So we've got 2 different ways of saying it. The first one, as one goes up, the other goes up. As one goes up by 1, our independent variable, then our dependent variable goes up by whatever that B1 is. And I'm going to say it the second way based on the, what is this called? The bullet 2. Based on bullet 2, we see here I'm using the same terminology. All I did was flip it and say the second part first. That's it. So you can say it this way in the second bullet. You could say it this way in this bottom second bullet, or you could say it this way, or you can find another way to say it, but just say it the right way. So for each unit increase in pay grade, for each 1 unit increase in pay grade, right? For each 1 unit increase in pay grade, federal employees earn expected change in their salary, right? In their Y, which is salary, is that B1, 4779. So it's really that straightforward. And if you just come back to the slide if you need to, but it's really that straightforward. Okay? All right, so let's take a look. I want you to pause. Come up with the equation yourself. Remember, when you're coming up with this equation, you're not going to use generic terms because you have a name, I have a name. We all are given names in life. And so we're not going to say X, we're not going to say Y, we're not going to say B naught, we're not even going to say B1, right? We're going to say what we mean. So hopefully you've come up with this equation that expected salary equals -5132 or 33 plus 4779 times grade. We've already done this. So, and so now let's come up with an equation here. So I'm going to need you to pause, think about it, come up with it for yourself. All right, and hopefully this is what you came up with. Expected salary, we're still talking about salary, right, is 18,714 plus 502 times age, because age is what we see now, not grade, but age, right? So, question. Oh, I put the answer. So, question, which of these has a greater impact, right? For each unit increase in grade, right, as grade goes up 1 point, salary goes up almost $5,000, right? As age goes up 1, as every new year, you get a salary increase of 502, right? We're going to learn again in lecture 8 what strength really means in terms of these B1s. But we're going to learn in lecture 8 where to really look at strength, okay? And it's really here in our standardized coefficients that we're going to look at strength the way that we do with correlation coefficients. But for right now, we're going to stay with our unstandardized coefficients and just focus there because we need to learn it. Because again, it's a regression coefficient, so it's the most important thing, right? So as age increases by 1, employees earn $502 additional dollars, right? And so B1 is higher for grade than for age. So this means that expected salary increases more as grade increases by 1 than as age rises by 1. Okay? So now that we've learned this equation, we know how to come up with this equation whenever we have a regression output. We know every little part of this equation. We know what Y means. We know what that hat means, right? It's expected. We know what B naught means, B1 means, X. We know what all those things mean. I'm so happy. And so now, so now, oh, second thing we know is how to interpret all of those, right? We know how to interpret V naught, our y-intercept, because it's when x is 0. We know how to interpret our V1. It's how x changes y, right? If x increases by 1, that B1 is telling us exactly what happens to y. Boom. Okay. And so now we're going to calculate. We're going to do exactly what we said in slide 1. It's going to help us to make predictions. I mean, it already does, right? Because we know that as grade increases by 1, salary increases by 47.79. So we know that prediction already. But say I want to know the grade at 4. I mean, the salary, expected salary, if my grade is 4. If I'm coming in at a pay grade of 4, what should I expect my salary to be, right? So now we can actually do that plug-in. We don't plug in if I'm asking you for equations only. But if I'm asking you to make a prediction for me, then you take that equation that you wrote out, right? We take that equation that we wrote out, then we start plugging in. We plug in the expected salary at grade 4. The only thing here that changes is this. We take the word grade away. We put in 4 because we need some calculation to be done in Excel, and regular calculators don't know how to multiply grade unless it's a number, right? So we can see lots of predictions can be made. So if the lowest pay grade possible is a 3, what would the expected minimum salary be for a federal employee at pay grade 3? Very sadly, 9,000. Even salary pay grade of 4 is ridiculous. No one can live off of that unless you're a student who, you know, still gets financial aid or something, or lives at home with mom and dad. Ridiculous. So we have some policy things to maybe work on here, and that might include having livable wages. But come to my urban policy class and learn more about that. Okay. So one more thing that we'll learn about is regressions and dummy variables. Dichotomous variables have only 2 values. I'm talking to the choir because you guys already know that, and we know that we typically code them as 0 and 1. Okay, and if it's a dummy variable, something like what we see here, right? What would that variable name be? Hopefully, you're saying male, because male is the variable that has the higher value attached to it. So our 2 variables here in this bivariate regression, male or gender, and salary, right? Like, we know we call it male, but we know that the variable is gender. Hopefully we're aware that the variable is gender, and we're just calling it male so that we don't have to go in and put notes and all that type of thing, and it makes life easier as we're trying to interpret. Okay, so when the independent variable is a dummy variable, the y-intercept now magically has meaning. Why? Because it's a dummy variable. 0 means something. 1 means something. 0 means something, right? Before, a pay grade of 0 meant nothing because there is no such thing as a pay grade of 0. An age of 0 means absolutely nothing because there's no way someone who was just born, came out of the womb, is now a federal employee. So actually, let me take this back a little. So here, what would the y-intercept mean here? Hopefully, let me give you a second. Hopefully you're saying, pause it if you haven't gotten to it yet. Okay, just pause. But if you get to it, then you can unpause. Hopefully you're saying the y-intercept is telling me that a newborn, someone with 0 years of age, makes $18,000. Okay, hopefully that's what you're saying, which is unrealistic because a newborn isn't working in the federal government, at least. I mean, they might be getting some type of trust fund already ready for them, but not in the federal government. Okay, so but every year of increase that I make as I have each new birthday, then my salary is increasing by $502 for every year. So if you are 20 years old, then you can plug in 20 here and see, what would my expected salary be at the age of 20 for as a federal employee? What would my salary be maybe at 65, right? Yeah, okay. So let me go back to where I was. Okay, so we know some things now. We know what our equation would look like. Hopefully, we do know that. We know what our independent variable is, our x. We know what our dependent variable is, our y. It's the same thing, salary. We know what our y-intercept is, and we even know what it means. Another point here, before I even tell you what it means, is that the word mean, the word average, is what tends to be used for dummy variables in a bivariate regression. because there's really just two values, one for male and average for female. The average salary for males, average salary for females. If you were to take this regression and plot it out, it would literally only give you 2 points. That's why we say a mean, because it's the average of all the males and then the average salary for all the females. When you have grades, grade or age, you don't get just 2 points because there's lots of grades, right? And so you might get the salary here, the salary of that one, the salary of that. So they're all averages, but we still expect that we say expected rather than average or mean. Okay. I say all that to just so that you understand what happens in the mathematical or statistical or research world. But I say that also understanding that if you say expected, it's okay, because these are predictions, so it is expected, right? But in the sample, the mean, the average salary is right? In this sample, but it's still expected for the entire population, right? But for this sample, the average is yada yada. Okay. That's out of the way. So if you say expected, it's okay. All right, so the regression coefficient is interpreted as the difference between the independent variable with value of 0 and the independent variable with value of 1. We did that before. Hopefully you remember lecture 4, because we did that with correlation coefficients, right? If you have a dummy variable and a correlation coefficient, you better be saying both of the values of that dummy variable, because it's a comparison, remember? And so we're comparing males to females in this case, or blacks and whites, or promoted and not promoted, but we're comparing two things. I just realized you weren't seeing my hands, and I'm a hands person. Okay, so the regression coefficient is interpreted as the difference, right? The difference between this category and that category of the dummy variable. Okay, so interpretations. We've got very generic interpretations because we're going to build up to where we want to be. But the generic interpretation helps you to get there, right? The change in our y when x changes by 1. We already know, oh, you know what? I skipped something. We'll get to it. Okay, no, actually, let's do it now. Let's do it now. Let's not even skip to it. So bullet point number 2 and bullet point number 3 is what I skipped. I should have mentioned here, or I should have quizzed you here, what is your y-intercept? What does it mean? First off, our y-intercept is $34,222 or $23. But what does it mean? Because we just said with a smiley face that it's meaningful. So what is the meaning? Hopefully you're saying, well, if it's at 0, if it's when x equals 0, right? If it's when x equals 0, here's our x. What is x at 0? It's female. So our y-intercept is telling us that the expected or the average or mean salary for a federal employee is, for a female federal employee is 34,000, yada, 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 right? So that's what our y-intercept means in this scenario. Our y-intercept is means that the expected $34,223 is the expected salary when x is 0. Is the expected salary when x is 0. I need you to fill in the blank. X is 0. What do we see here? We see when x is 0, you're female. The expected salary of a female. Oh, okay. So now let's go down to these interpretations, because we're now going to interpret our B1, And we know generically it means the change or the difference in y when x changes by 1. Okay? Less generic, the change or difference in the mean salary when gender. See, now we're not saying x's and y's, we're calling it a little less with the generic gender and salary. So the change in our average salary when a gender variable changes from 0 to 1, right? It changes by 1. There's only one thing it can change from, 0 to 1, 1 to 0. So as it increases by 1, right? That's what it's doing. In the first scenario, changes by 1, increasing by 1. And what does that mean in this particular dummy variable scenario? It's increasing from female to male. So the expected change, or the change in our mean salary when gender changes from female to male. And the best way to say it, got a couple of ways. Well, two ways. The difference in mean salary, the change in mean salary, right, between men and women is 12,777. More specifically, men make 12,777 more than females. And you know how we know that? Well, let's look at the next slide. Okay? So here's our same equation, same output. Same output. I'd like an equation though. So let's plug in an equation. I'm going to give you a second, pause it so that you can come up with it on your own. But I'm going to go for it. So the equation is expected or mean salary equals 34,222.795 plus 12,776 times male, because that's the variable name. Okay. So now I ask, what is the y-intercept? Well, hopefully you're saying right off the bat without much thinking, because you know it says constant and right beside it, or it might say intercept. So there's no guessing. It's 34,223. Boom, done. So here's a question. Next question. What is the average salary for women? Well, listen, professor, I have an equation before me, and so I'm just going to plug this equation in and give you your answer. So hopefully you're plugging the equation in with male, right? Male should be now 0 because that's women. So that means that whole thing goes away. So really, it's the same thing as our y-intercept, because 0 now means it's the y-intercept, okay? So y-intercept, that's what we're looking at. So our y-intercept, same thing as our average salary for women. And we were able to do that whether we looked directly at the output and just knew it right off the bat because we're comfortable with this output now, right? Or we used the output that we're comfortable with and created an equation that will never let us down, and we just plugged in 0 because that's what we wanted. We wanted female. Okay? So then my question, you know what it is. What's the average salary for men? Well, hopefully, since you already know how to plug and chug, you're plugging in instead of 0. The code here says 1, so you're plugging in 1. So the salary for males is what we said in the previous slide, is $12,000, almost $13,000 more than females. Again, another policy issue we need to work on. But so hopefully what you're doing here is taking your 34,000 plus your 13,000 that you multiply by 1, which means it's just that, right? And you're getting 47,000. So women on average in the federal government, this is 1998 data, 34,000 was their average salary. For men, 47,000. So a good $13,000 difference. So that's really everything about bivariate regressions. And that's really the most basic thing and the totality of understanding bivariate regressions. But I want to throw one more thing at you, because I think what you're asking now is, well, what if I recoded and I coded differently? What if I said the variable name is female? Hey, I got you. I got you covered. The variable name is now female. So hopefully, if you coded this as female, you're saying female equals 1 and male equals 0. If you're saying that, right, then what's our equation? Hopefully, we're coming up with that equation, right? 46 or 47,000 minus 12,777 times the variable name female. So the point that I want to make here is that dummy variables can be coded however you want to code it, okay? But the regression will still give the same exact expected values. As long as you code it correctly and you interpret correctly, all is well. It doesn't matter that we didn't code the same. And here's why. So we see different numbers, right? That for 34,000 that was up here at the top is now 46,000, but guess, 47, but guess what? But this is also different, right? But that's not the only thing that's different. We've got a negative here where we had a positive here. So let's go and break this down and answer these questions again. So what is the y-intercept for this? Hopefully you're saying 46,000, because last time you said 34. What does that mean? Well, hopefully the next question helped you answer that. Or I guess it would be this one, because if female is 1, male is 0, so we would plug in 0, right? We plug in 0, so our male salary is $46,000. Our male salary is the y-intercept, is when x equals 0, our male salary, right? And I say expected here. Of course, we know it's mean, expected, yada, yada, tomato, tomato, okay? What we don't do is say mean for things that we should say expected for. We don't do that. Don't do that, don't do that. Okay, so we learned already that our y-intercept is different, but it's telling us the exact same story. It's telling us that the mean salary for a man is 47,000, the mean salary for a woman, right? You take 47, you subtract that 12,777, and you should get that 34,000 that we initially saw in the previously, in the above output, right? Coded differently, same results. And so much so that we can even interpret this regression coefficient all by itself, right? We can see that 12 females, we can see females make $12,000 because of this negative. We're saying less. Females make 12,777 less than males. Females, this, that. We're going backwards. Just like we said, males make that much more. Males make that much more, right? Males make 12,777 positive, so that's more. Females make 12,777 negative, so that's less. Same story, same story. So we're done with lecture 1. I hope you, lecture 6, I hope you enjoyed it, and I hope it made total sense. We don't want, you can move on to practice exercises. I provide a lot of them this time around, more than I usually do. You wouldn't know that, but more than I usually do, because I really want this to get in your system, because what we're going to do for the rest, for lecture 7, for 8, for 9, is continue on, but we have to get the basic before we can move on to knowing what all these other columns mean. But by the end of lecture 9, we will know what everything means in this regression output, and more that I haven't even shown you yet. Surprises to come. All right, enjoy your your practice. Bye-bye.